Alright, so last time we introduced the CK machine, and the CK machine is really going to be the framework that we're going to focus on for developing new kinds of programming languages. However, our languages right now are really quite boring. And the reason they're quite boring is that they only have numbers, well, constants, if statements, and primitive function calls. Well, it would really be nice if we had some way for users of our programming language to define their own functions. And so that's what we'll do today. We'll define a new language called J2. And in J2, it is going to have more advanced features. So programs in J2 will be indicated by program. And they will start with a sequence of Ds, which are definitions, followed by a single expression. And what a D is a definition of a function, f, that has some number of arguments and then one body expression. If we look at our expressions, they are either values, they are applications, or they are if statements, or they're one more thing, and this is new, and that is a variable x. Values are either numbers, booleans, primitives, or the names of functions. And x is some set of variable names, and f is some distinct set of function names. Now, in your implementation, this right here is going to be some sort of data structure called like variable reference. And this right here is going to be some other data structure called, for example, function reference. And they may in fact both be strings. What we're going to do is we're going to have it so that functions, f's, always are capital letters, and variables are always lowercase letters. Things like this are pretty common in different programming languages. For example, in the language Haskell, variables are always lowercase, and types are always uppercase. So here's an example program in this language. We could write define double x plus xx, and then double plus double 1, 3. So this would be an example program. So here's one definition, and here's the main expression. And we would call double once and get 2, add 2 and 3 and get 5, call double again and get 10. Now, a kid is banging on the door. Hold on. All right. Okay, so here's one example program. Let's imagine that we didn't have this line. We could add another definition. Let's call a function called quad. And let's say that it's double of y. And then our function could be something like quad of plus 1 double 3. Okay, so this program would have two definitions and then one main expression. So this is what we're adding to our language. Okay, so how can we understand what these programs mean? Well, the first thing to understand is make an analogy to normal math. So in normal math, imagine I wrote the following. I wrote f of x equals 1 plus x. And then I asked you, what is f of 3? I could go downstairs and ask one of my kids right now how to do this. Well, what they would say is that what you do is you take this f and you take the 3 and you plug it into the x. And then you find all the places where x appears and you replace them as 3. So therefore f of 3 is equal to 1 plus 3. And then now you have a normal equation that you then just evaluate like normal, and you get 4. Okay? And similarly, if I were to ask what is f of 3 plus 4, probably what they would say is, well, wouldn't it be simpler to first write down f of 7 and then plug that in and get 1 plus 7 and then get 8. So the key thing that functions give us variables and substitution. And substitution is really the most important thing because it's what gives functions their life. You know what I mean? It makes it so that they actually do something. Okay, so the first thing to do is to define exactly what this substitution operation means on our language. So recall, actually, I just wrote it down. So here's what our e's are. So what we want to do is we want to write a function called subst. And what it does is it takes a variable and an expression. Actually, I guess it takes a value, a variable and a value, and an expression, and returns a new expression. So for instance, if we call subst with x and xv, and we give it a value, then we just get back the same value because there's no variable inside of there. If we call subst on x, xv, and some variable like x, then we would get back xv. But if we called it with a different variable y, then we would just get back y. If we called subst and we gave it an if, ec, et, ef, then what we would do is we would get back an if where we would call subst on x, xv, and ec, then subst again on x, xv, and et, and then one more, subst x, xv, ef, and so on. So the main thing that substitution does is it just walks through the entire term, the entire program expression, finds all the variables. If they match the variable it's looking for, then it replaces them with a value, otherwise it leaves them alone. So this is a very simple function to write, and you can go write that function in your high-level language, and you can write it in your low-level language. We can then talk about how to extend our interpreter, like our big step interpreter and our small step interpreter, how to extend them to deal with this new feature. Let's first talk about how to extend our evaluator, our big step interpreter. So it used to be that our big step interpreter would take an e and return just a value. But now our big step interpreter needs to know what all the functions are. We're going to call that value delta. And basically what delta is it's a map from function names to definitions. And the main thing that we need to do is if we ever call interp and we get a function call with some variables v0 through vn, then what we need to do is we need to call interp on, I don't like where I'm writing that. We need to call interp with the same delta on the body, okay? But it's the body after doing substitution, so we'll call that body prime. And then we'll say where e body prime is equal to substitute. Let's imagine that we have a version of substitute that operates on a whole bunch of things. We'll call it substitute with an arrow on top. On on x 0 xn, and v0 dot 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 vn and e body, where define f of x0 through xn e body is equal to, if we look up inside of the map, the function f. So what we do is that if we ever call interp on a function call, we're going to take the name of the function, look it up inside of delta, see that there's a function there, make sure that it has the same number of arguments as the arguments that we've been provided, and then substitute each one of them inside of the body, pull out that new body prime, and call interp on it. Okay? So that's how we can adjust our big step interpreter. The next thing that we want to do is we want to talk about how to change our CK machine to work with this. So this new thing will be called the CK1 machine. We used to have the CK0 machine, now we have the CK1 machine. And the main thing that's going to be different about it is that we are going to add 2 extra rules. 2 extra rules? No, I guess just 1 extra rule. So the 1 extra rule is going to say that if we ever end up with a value vn, and we have a k-app where there's a whole bunch of values, v0 dot dot dot, and then the last one is a function call, and then there's no more, expressions, and then there's a k. Then what we want to do is we want to go to e body prime with the continuation being k, where e body prime is equal to subst, the arrow version, which we can implement in the low-level language just like we can implement it in the high-level language, x0 dot 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 xn through v0 dot 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 vn on the e body, and where define of f x0 dot 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 xn e body is equal to looking up inside of delta the name f. Now what's delta? Delta is just another argument to your CK. Your CK0 used to take e and return a value, and now CK1 is going to take delta and e and return a value. And so it's just going to have a data structure that's just the map. If you're using a fancy language like C++ or Java, there are map libraries that you can use, like a hash map, that kind of thing. And if you want to be boring like me, then what you can do is you can just use like a linked list or whatever. Okay. So let's look at an example of that. Hold on 1 second. Ah, yes. Okay. Let's look at an example program running on the CK1 machine. Okay, so suppose we have this program. Define double x plus x double 1. Okay, so how do we turn this into, how do we inject this? When we inject it, we get delta is equal to double goes to define double x, x plus x, and of course that is just, a data structure. There's a data structure called define that has 3 fields: the name, the list of arguments, and the body. Okay, and then our initial state is double, double, 1, and k-ret. Okay, then we apply rule 4, I believe, and we focus on double, and we have a k-app with no values, and then double 1 as 1 argument, and then the k-ret. Okay, and that's rule number 4. Then we have rule number 5, and so we focus on double 1, where our k-app is double, and then no other expressions in the k-ret. Then we use rule number 4, and we look at double. Remember, double is a function variable, a function name, so therefore it's a value. Then we have k-app, no variable so far. First argument is 1, and then inside that we have another k-app that has the function value 1, double, no more arguments, and then the k-ret. All right, and then now we use rule 5, and so now we focus on the 1. We have k-app, double, no more arguments, k-app, double, no more arguments, k-ret. All right, now at this point, we have a value. We have a sequence of values that ends in a function call, in a function name, and then we have no arguments. So therefore, we can use this new rule right here, which I guess would be rule 7. So we use this new rule, rule number 7, which requires us to do a few things. We first have to look up double inside of delta, and we'll get this. Then what we need to do is we need to call subst. So we need to call subst on the body. The body is plus xx, and we're calling it with the arguments x, that's the argument name, and then the argument value, which is 1. And so then that gets us plus 1, 1. And so we then have plus 1, 1, and then this original continuation, k-app, double, k-ret. So notice that an interesting thing happened here. There's no rule inside of the new CK1 machine for what happens if there's a variable in this spot. And that's because a variable doesn't have any way to evaluate it. There's nothing that you need to do. And the reason that there's nothing that you need to do is because subs gets rid of all the variables. So anytime a variable shows up in that position, then it must have been an unbound variable that didn't get substituted away. All right, so now at this point, we would do, rule number 4, rule number 5, rule number 5, rule number 6, and eventually we'd get a 2 here, and then k-app double, k-ret. Okay, so this would be rule 4, 5, 5, and then 6. 4, 5, 5, 6, yeah, okay. And then we have another instance of rule 7, where we would get plus 2, 2, and then we would just have k-ret. And then we would have another use of rule 4, 5, 5, 6, and then we get down to 4, k-ret, and then we'd be done, and we'd get the answer, which is 4. Okay, so that's a walkthrough of running this particular program. Since my videos in the morning, I got a sunburn. Look at that. So annoying. Okay. There's a few interesting things to say about this new system, CK1. Probably the most interesting thing is the way that it teaches us about how function calls and stacks interact. So, recall that the K structure is implemented by a stack in many languages. Okay? The K structure is implemented by a stack in many languages. Now, if you're using a language like JavaScript or Java or Python, try to write a program like this. So I'm going to write a program in Java. So I'm going to write class test. And then there's going to be a function. That's going to be a static function. It's going to be called static int f. And it takes one argument, x. And what it does is it's going to return f of x. And then we're going to write public static void main. And we're going to do return. Sorry, we're not going to do return. We're just going to call a function. We're going to do f of 0. Okay, so if you go write this function, you can go write it right now. So if you go write this function and try to run it, you're going to get an error. And the error is going to say stack overflow. And then it's going to say f, 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 f. It's going to print that out many, 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 many times. What is the reason for why it does this? The reason why it does it is that many programming languages, what they do is they make it so that when you call a function, you create a stack frame. And by calling that function, you create a stack frame that then consumes space. And what this program does is it has a function call that then calls another function. And that calls another function and calls another function. And so each one of those, what it does is it requires more and more space. And eventually we use up all of the memory that was set aside for the stack in the machine. Now, let's look at this exact same program in our language. We would write it like this. We would write define f of x, f of x. And then we would call it with f of 0. So let's see what happens in our language when we try to run this program. Well, what would delta be? Delta would be a mapping that said that f goes to define f of x, fx. Okay? We would inject, and so we would get f0 and then kret. All right? Then we would focus on f, and we would have a kapp that had no values, and then 0 as the next expression, and then a kret. Then what we would do is we would focus on the 0. We'd have a kapp of an f, and then no more arguments, and then the kret. Then what we would do is we say, aha, there's a value there. That value, and then there's a function. So what we need to do is we need to say, what is delta of f? And we would get back, define f of x, fx, okay? And so then we would put in here subst x with 0 in the body fx, and then the continuation would be kret. And then that is just equal to f of 0 kret. Now notice that this is now a loop. We did this, and then that, and then that, and then that, and now this goes back to here. So notice that this program is an infinite loop. It does take infinite time to run, but it takes finite space. And the reason why it takes finite space is that when we call the function, that's when we actually remove a frame from the stack. This is very different than the way that Java and JavaScript and Python and C work. What they do is when you call a function, like right here and right there, you push on a stack frame. But in our language, we actually remove a stack frame when we call a function. What's going on here? The thing is that we have correctly implemented function calls. Other people, programming language implementations, they incorrectly implement function calls, and they make it so that function calls consume unnecessary space. Now, some people have realized that what we've done right here is the correct way to implement functions, and they call the behavior that we've done, they give it a special name, they call it tail call optimization. But this is a very inaccurate name. The reason why it's inaccurate is because optimization sounds like something that is optional, that is an interesting idea, some sort of optional step that makes programs slightly better. But actually what we've shown is that the incorrect behavior that does not come from the mathematical explanation of it leads to arbitrary memory usage and stack overflow. It makes it so that a program that used to use a constant amount of memory now uses a linear amount of memory. So instead, the correct term for this is called proper function calls. Function call implementation. Proper here, implementation. Proper here meaning correct, meaning not having any mistake. And so there are quite a few languages that have proper function call implementations, such as Haskell, Racket, ML, Scheme, and so on. This is a very important point that many people do not realize. All right, so I think that should be enough for today. Maybe one more thing to note is that do notice that our language allows us to write recursive functions like this. It allows us to write functions that are mutually recursive, where one can refer to the other, because this delta thing is this global, this global value. So, I guess that's it, and we will continue next time with another topic.